Welcome to the E-Pathshala lecture series in computer science. We are dealing with the course computer architecture. This module deals with the floating point arithmetic unit. So, the learning objectives for this module are to discuss the standard representation for floating point numbers and show how the various arithmetic operations like addition, subtraction, multiplication and division are carried out in the floating point unit of the processor. So, first of all we look at the need for floating point numbers, look at why a standard representation is needed and what is the standard representation for floating point numbers, and then move on to the various arithmetic operations of addition, subtraction, multiplication and division. All of you all know the scientific notation that is used for real numbers. So, you have the sign of the number and then you have the mantissa part, which includes the whole number part and the fractional part, and then you have the radix or the base of the number. For decimal numbers, of course, it is 10, and then you have the signed exponent. And floating point numbers are normally normalized, so that you have a standard representation. So, you know that a number can be written as 35 point something or 3.5 something, and the exponent value can be adjusted. So, in order to have a uniform representation, we go in for normalized representation, where if you look at decimal numbers, anything between 1.0 and 9.9999 in decimal is normalized. So, you do not write it as 0.0. So, you need to have a significant digit and only one significant digit to the left of the decimal point. Similarly, if you are looking at binary numbers, because binary has only 0 and 1 in the number system, obviously you can't have a 0 point something, it is a 1 point something. So, that is the normalized representation in binary, and this normalized representation obviously simplifies your floating point arithmetic operations and comparisons. To show you an example here, 5.6745 into 10 power 2 is a normalized representation. Similarly, 1.23 into 10 power minus 19 is a normalized representation, whereas if you look at 345.67 into 10 power 8 or the other numbers that I have shown here, they are obviously not normalized, because you have more than one digit or you have a 0 to the left of the decimal point. So, in binary format, if you look at the normalized representation, it is minus 1 power s into 1 point m, where 1 is the implied 1 to the left of the binary point, m is the mantissa, into the base of the number system, which is 2 for the binary number system, and the signed exponent. And this leading 1 that you have is normally not part of the representation, because it is always going to be 1 point something. This 1 is just implied and you do not have to represent this as part of the representation. So, representing a wide enough range of floating point values with enough precision, that is decimal places, given the number of limited bits, is our aim. So, when you look at the trade offs that you have to do here, if you have more number of e bits, it obviously increases the range, and more number of m bits increases the precision of the number system, and a large b or the base of the number system, the radix of the number system, increases the range but decreases the precision. And you always know that the distance between consecutive floating point numbers is not constant. And when you look at the exponent representation, normally you know that when you go in for signed numbers, negative numbers are always represented using the 2's complement representation. But if you look at the floating point representation here, when you look at the biased signed exponent, it does not go in for the 2's complement representation. Instead, we use what is called the biased exponent notation. All of you should be familiar with what is called an excess n representation, or rather excess 3 representation. You would have studied an excess 3 code. Now, it is similar representation here, except that instead of 3 you use other numbers here. When you look at, for example, when you have a bias, whatever that bias is, that bias gets added to your exponent value. So, if your bias is 127, for example, whatever exponent value you have, suppose if it is 5, that 5 is added with the biased value, and only then you represent the exponent value. So, if you have to find out the actual exponent value, you have to subtract the bias. So, for example, here when you have a 1 1 1 etc. all ones, that represents the most positive exponent value, and all zeros represents the most negative exponent value for sorting and comparison purposes. Rather than looking at a 2's complement representation, when you go in for a biased representation and when you have all zeros representing the most negative and all ones representing the most positive value, it becomes very easy for sorting and comparison purposes. So, that is why we go in for a biased exponent representation. And because we use a biased exponent notation, to get the correct signed value for the exponent, you need to subtract whatever bias value you added. So, biased floating point numbers are normally used, and they are of the form minus 1 power s into 1 point m into the base power e minus bias. E is the actual exponent value, and because you added the bias, you have to subtract the bias now. For example, suppose if we assume 8 bits for the exponent representation, the bias is given by 127, that is 0 followed by 7 sevens. So, the largest exponent value represented by this is all ones, which is 255 minus 127, which is 128. Similarly, the smallest exponent value is represented by all zeros, which is nothing but 0 minus 127, which is minus 127. So, the range of numbers that you can represent, the range of exponent values that you can represent is my actual numbers is minus 127 to plus 128, and the exponent biased exponent values change from 0 to 255. So, if each one follows different representations for floating point numbers, you do not have portability across different machines. We know that every floating point number has to have a sign bit, it has to have a mantissa part, and it has to have an exponent part, and now we have decided that it needs to follow the normalized notation, and it should have a biased notation for the exponent value. But there are different ways of representing all this information, and if each one is going to represent it in a different form, you will not have any portability across different machines. So, there is a standard representation for floating point numbers, which is given by your IEEE 754 standard. This obviously improves the portability of scientific applications. So, the base of the number system is assumed to be 2, and you have a standard representation for single precision floating point numbers, and similarly for double precision floating point numbers. For a single precision floating point number, you have a 32-bit representation where the S bit represents the sign bit 1 or 0. 1 indicates that it is a negative number as usual, and 0 represents that the number is positive. You have 8 bits which are used for the exponent representation. The exponent, as I indicated earlier, you go in for the biased exponent representation, and the remaining 23 bits out of 32 bits are used for representing the mantissa, and the mantissa is again represented in the normalized form. That is, the mantissa is brought to the form of 1 point something, that 1 is implied, and the numbers that appear to the right of the decimal point or right of the binary point alone are given here. Similarly, when you go in for the double precision floating point representation, you have a 64-bit representation, again 1 bit for the sign bit indicating whether the number itself is positive or negative, 11 bits which give you the biased exponent, and 52 bits which give you the mantissa in the normalized form with an implied 1. So, the exponent bias is 127 for single precision floating point numbers, and for double precision floating point numbers it is 1023. So, the floating point numbers are of the form minus 1 power s into 1 point m, because 1 point m because it is the normalized representation, into 2 power e minus bias. 1 in the mantissa and base of 2 are implied, they do not find a place in the representation, and this is the representation for your single precision floating point number. And if you have a number as given here, the value of that number is indicated by the number that has been given below. So, this gives you an example of how to do the representation. This is the standard representation for your floating point numbers as already discussed. So, if you have to represent a number like minus 1.5, how do you represent this? Minus 1.5, you know the sign of the number is negative. So, you have 1 which indicates the sign bit as negative, and then you have this is a 1 minus 1.5. So, you do not, when you convert it to binary, this is 1.5 in decimal. So, when you convert it into binary, it is going to be, this is going to be converted to 1 and 0.5 is going to be converted this way. So, you have a 1 0 0 0 indicating that it is 0.5, and as far as your exponent value is concerned, it is going to be minus 1.10 etc. into 2 power 0. So, to that you will have to add your exponent value of bias value of 127. So, when you add that, this becomes your exponent value. So, this is the biased exponent value, this is the normalized mantissa value, and this is the sign of the number. So, this is how you represent minus 1.5. Similarly, if you have to represent a 0, 0 is represented by a positive sign here, all zeros for your exponent value and all zeros for your mantissa value, and the exponent value, as you know, lies from 0 to 255. Similarly, if you have a number like this, the magnitude of the numbers that can be represented using this representation are in the range of 2 power minus 126 1.0 into 2 power 127 2 power minus 223, which is approximately this number, this range. This is yet another example. So, if you have to represent minus 1.5 into 2 power minus 126, then this is how the representation goes. So, examples in normalized format. So, if you have a the smallest number, you can see that this mantissa is in the normalized format because it has a 1.0000 something. So, if this is the number that is given, then that is equivalent to a 1 into 2 power, because the exponent value is 1 here, the actual exponent value is 1 minus 2 power 2 power 1 minus 127. 127 is the bias that you initially added. So, you are subtracting 127. Similarly, this is the representation for 0, and the largest value is represented by this, where you get to have a positive number. This is the biased exponent value, and this is 1 point followed by all ones, which is represented by this number. So, similarly, if you have to represent anything else, you can always find out what it represents. So, minus 1.0 into 2 power minus 1 is represented this way, and 0.75 into 2 power 4 is represented this way. Now, apart from the normal representations, you have a range of 0 to 255. Out of that, 0 and 255 are used for other reasons, and only 1 to 254 are used for normal representations. The other two representations are used for special encoding. So, the special encodings are used to represent unusual events. So, plus or minus infinity for division by 0, not a number representation for the results of invalid operations such as a division of 0 by 0, and true 0 is represented as a bit string of all zeros. So, this is the general representation. So, you have beyond this, it is an exponent overflow, and beyond this it is an exponent overflow here again, and this is the range of representable negative numbers. This is the range of representable positive numbers, and within this range you have the denormalized numbers, where it is a gradual degradation here, it is a graceful reduction, and it indicates an exponent underflow. So, this denormalization allows for representation of very small numbers. It is identified by the exponent value being equal to 0 and having a non-zero mantissa part. So, the format is minus 1 power s into 0.m into 2 power minus bias minus 1. So, the smallest possible double precision denormalized number is given by this, and the smallest positive double precision normalized number is given by this. So, if it is normalized, it is going to be 1.0 into this. If it is denormalized, it is going to be 0.0 into this. So, this gives you the summary of floating point representations. So, for single precision, you are going to have an 8-bit biased exponent representation, and the fractional part is a 23-bit fractional part. For double precision, you are going to have 11-bit biased exponent part and a 52-bit fractional mantissa part, and if the exponent part is all zeros and the fractional part is also zeros, it represents a true 0. and if your exponent part is all zeros, your fractional part is non-zero, then it represents, depending upon the sign of the number, it represents a plus or minus denormalized number. Similarly, if it is this range to minus plus 127, that is plus 127 to minus 126, that range is the normal representation used for normal floating point numbers. Similarly, if the exponent value is all ones and the mantissa part is plus 0, it represents plus or minus infinity, and the last case where the exponent is all ones and the mantissa part is non-zero, then it is used for representing what is called a Norton number, which is normally used for representing unusual events like divide by 0. So far what we have looked at is, we have looked at the need for having a standard floating point representation. What are the various values that need to be represented in a floating point representation? We have looked at standard floating point representations for both single precision and double precision floating point numbers. Now, we look at the various floating point arithmetic operations. So, first of all, we look at floating point addition operation. So, when we are looking at arithmetic operations and we are looking at particularly addition operation first, you know how to add two floating point numbers. Suppose if you have a number 1.5 into 10 power 2 and another number some 3.5 into 10 power 5, one is a 10 power 2 and the other one is a 10 power 5, you obviously can't add both of them together. You first of all have to make the exponents same. Either the 10 power 2 has to be converted to 10 power 5 or vice versa. So, the exponents will have to be made the same. So, the same rules are applied when you go in for binary floating point arithmetic also. So, we are looking at floating point addition of numbers represented in the standard form, which we already discussed. So, first of all, you will have to make the exponents the same. So, when you are making the exponents the same, you have two options, because two numbers, one of them will have a larger exponent, the other one will have a smaller exponent. You can either take the larger exponent and shift its mantissa so that the exponent becomes smaller, or do it the other way around, but we always take the number with the smaller one and shift its mantissa to the right until the exponents batch. Otherwise, you lose the most significant bits if you do it the other way around. And this, when you are doing the shifting operation, remember that it is a normalized representation. So, you have an implied 1 to the left of the binary point, and that 1 will have to be taken into consideration when you are doing the shifting operation. Once the shifting is done and the mantissas have been equalized, you will have to add the mantissa and then choose the larger exponent, because you have already shifted it in such a way that the mantissas are equal to the larger of the two exponents. You will have to choose the larger exponent, and now put the result in normalized form. So, in order to put the result in normalized form, you will have to shift the mantissa left or right until in form 1.1, adjust exponent accordingly. Handle overflow or underflow if necessary, and then finally, you will have to do the round off operation, and if necessary, you will have to do a renormalization operation, because the rounding would have produced an unnormalized result. So, as usual, however you will do a decimal floating point addition, equalize the mantissas by shifting, add the exponent values, then tentatively fix the exponent of the result, and then do your normalized operations and rounding off operations. Now, this is the algorithm that I discussed earlier. So, this is best illustrated with an example here. So, you have the two initial values. So, first of all, compare the exponents, identify the smaller exponent, and you know the difference between these two exponents is 2. So, you will have to once you have identified that this is the smaller exponent, take this mantissa and shift it right by 2 bit positions. So, this is the shifted value, and while shifting, remember that you will have to take the 1 into account. So, this is the shifted values. After having shifted the values, you will have to add both the mantissas and the addition operation, and you know the exponent is taken as the larger of the exponent. So, tentatively you fix this as the exponent value and check whether the result is already available in the normalized form, or you will have to normalize it further. If it is not available in the normalized form, you will have to normalize it, but here you find that the final answer is already normalized. So, that is the result. So, this is the hardware design for floating point addition operation. So, this is the general architecture of a floating point arithmetic unit, addition unit. So, this unit, the smaller ALU takes in the two exponent values, this exponent and this exponent's value. It does a subtraction here and finds out which is the larger of the two, and it also finds out by how much it is larger. So, that information is passed on to the shift unit here. So, the shift unit will decide which of the mantisas or significance is to be shifted. See, to the ALU here, the big ALU here, one significant or one mantissa part goes as such, the other mantissa passes through the shifter unit and then comes here. So, whichever has a smaller exponent value, that information comes from the small ALU that decides which of the two mantissa values is to be shifted. So, one comes straight, the other one moves through the shifter unit and comes here, and then the control unit decides whether it is to perform addition or subtraction operation here. It does the addition or subtraction operation here, and then it passes on the result here. Now, here you check for any zeros, whether it is available in the normalized form or not available in the normalized form. So, if it is not available in the normalized form, you will have to normalize it. So, normalize it, and after doing the normalization part, rounding is required. Now, what is meant by rounding is, normally when you look at floating point operations, you do not just operate with exact number of bits. In order to maintain the precision of the number, you always add a few bits which are called the guard bits. But once the process is over, finally the result will have to be given according to the standard. So, rounding off basically removes off the extra bits that you added and produces the result in the proper format. So, this is the sequence of operations. So, this is the comparison that happens, and then depending on which one is smaller, shifting operation happens here, and then the actual arithmetic operation is handled here, and then the normalization of the result is handled in this part, and rounding of the result happens here. So, finally, the rounded result is produced in the standard format. So, these are the various steps that will have to be done for floating point addition operation, and this is the final architecture. Now, the next one is subtraction can be handled in the same way. So, we do not have to discuss subtraction, because you know addition or subtraction you can always handle it depending upon the sign of the two numbers and depending upon which mantissa is larger and what operation is to be performed. You can always decide whether addition or subtraction is to be performed, and that can be done. So, the next floating point operation, arithmetic operation that we discuss is multiplication. So, when you have two operands represented in the standard form, remember that both the operands are available in the excess end notation or the biased exponent notation. So, in order to find out the results exponent, what you have to do is add the exponents and subtract the bias from the sum. Say for example, if one exponent value is 5 and the other exponent value is 2, what you would have done is you would have added 127 to this exponent value, and the bias of 127 would have been added to the second exponent value. So, when you just add both of them, you have 227s added. So, obviously, you will have to subtract 127 from it, only then you will get the result in the biased exponent form. Biased exponent is the actual exponent is 7, but you will get 127 added to it because it is in the biased exponent form. So, once this operation is done, do the usual multiplication operation. We have already studied multipliers. So, a normal multiplier is used for multiplying the mantissas, and once the multiplication process is over, the result may not be available in the normalized form. So, you will have to put the result in normalized form. So, for that you will have to shift the mantissa left or right until it is in the normalized form of 1.1, and then accordingly adjust the exponent value. And finally, you will have to decide whether there is an underflow or overflow occurring, and then do the rounding off operation, re-normalize if necessary if the rounding has produced an unnormalized result. And for the sign of the operands, if both the operands have the same signs, then set the sign bit is equal to 0, indicating that it is positive, or if the signs of the two numbers are going to be different, then as usual set the sign bit to be 1, indicating that it is a negative operation. So, this is an example that has been shown, and this is the algorithm that we have. the algorithm that I discussed, and this is an example. So, these are the initial values, these are the two exponent values. So, you will have to add the exponents first of all and then subtract the bias value and then multiply the mantisas, renormalize by shifting the number by 1 bit position and adding 1 to the exponent value, that is the renormalization done. And then because the sign bits are different, one has a 1 and the other one has a 0, the sign of the result is going to be negative. So, set the sign bit and produce the result. So, the next operation is floating point division. For floating point division, again remember that the numbers are represented using biased exponent representation. So, when you just subtract the exponents, because when you have to divide two floating point numbers, all you have to do is you will have to subtract the exponents. So, when you subtract the exponents, you know that you will get the actual difference between the two exponents, because one is a 5 and the other one is a 2 exponent values. When you subtract both of them, subtract 5 and 2, 2 from 5, you will get a 3, but 3 you will get an actual value of 3, but that has to be represented in the biased exponent form. So, you will have to add 127 to it. So, in the case of a division operation, you will have to subtract the exponents and then add the bias. So, you put it back into the standard format. Now, divide the mantisas. So, as usual, do a subtraction of the exponents, divide the mantisas, put the result in the normalized form by shifting the mantissa left or right until it is in the form of 1.0, 1.m something, adjust the exponent accordingly. And if you have overflow or underflow, you will have to handle it. You will have to do the appropriate rounding operation, renormalization if necessary, if rounding produced an unnormalized result, and as usual sign bits. If the sign bits are the same, set a sign bit of positive. If the sign bits are different, make the result negative. Now, what do we mean by rounding operation here? All along we have been talking about rounding. So, we will just elaborate a little bit on the rounding operation. Now, floating point arithmetic operations may produce a result with more digits that can be represented in your standard format. So, that is what I said, you are looking at having more number of bits, which are called the guard bits, which are essential in order to maintain the precision of the number. But finally, the result must be rounded to fit into the available number of m positions, and this is a trade off of hardware cost, keeping extra bits, and speed versus the accumulated rounding error. So, this is an example from your decimal multiplication. So, you know that when you do a normal rounding off operation, you know how the normal rounding off happens. So, this value is rounded off to 3.34. So, you can, this is examples of rounding operation, and when you do a rounding operation, you know that renormalization may be required after rounding. Now, the same way, just like how we do normal rounding off operations, you will have to do normal rounding off operations in the case of your floating point numbers also. So, this is an example for binary multiplication. Always remember that when you multiply two numbers with n bits, the result is going to have 2n bits. So, the result has twice as many number of bits, and the results that you get will not be available in the normalized form. You will have to normalize it, and the extra bits that you have will have to be removed off in some way. Rounding will have to be done. So, this is an example here. When you do a 1.10 into 1.01, you get a 1.111, and this may require renormalization after rounding process happens. So, in binary, an extra bit of 1 is halfway between the two possible representations. For example, here 1.001, which is a 1.125, you know, is halfway between 1.00 and 1.01. Similarly, a 1.101 is halfway between 1.10 and 1.11. So, how do you do the rounding off process? There are different ways in which you can handle the extra guard bits that you have. One easiest solution is just do the truncation. Whatever extra bits you have, just remove all digits beyond those supported. So, suppose if I need to have only 2 bits, then remove all these 3 bits and make it 1.00. That is one option, that is the easiest option. The other one is round up to the next value. So, if it is 1.001, then just round it off to the next value upwards. So, it is 1.01. The next one is irrespective of whatever you have here, round down to the previous value. So, it is 1.00. Now, both of these differs from truncate for negative numbers, but what is normally done is rounding off to the nearest even number. So, rounds to the next even number, the one with an LSB of 0. So, 1.00100 is rounded off to 1.00 and 1.01100 is rounded off to 1.10. This is the default mode of operation and it produces 0 average bias. So, this rounding mode is what is very frequently used, and in order to do this you will have to have what is called a round bit, and you need to have what is called a sticky bit, which is the OR of the bits to the right of the round bit. So, this indicates this is where you are going to stop, this is the round bit, and these indicate the OR of these bits indicates the sticky bit. So, depending upon the sticky bit, here the sticky bit is 1 because you have the OR of this is a 1, a 1.00100 is rounded off to 1.00. So, to summarize what we have done in this module, we have looked at the need for floating point numbers, we have looked at the IEEE standard for representing floating point numbers, both for single precision floating point numbers as well as double precision floating point numbers, and then we have looked at the standard steps and the architecture that is needed for implementing a floating point addition or subtraction operation, and the basic steps that are needed for doing floating point multiplication and division operations. And finally, we have looked at what are the different rounding methods that are used to remove the extra guard bits that are introduced in the architecture. Thank you.